Hello grade 11, welcome. In this video, we will focus our discussion on the exogenic processes, which include weathering, erosion, and deposition. Now let's get started. Our discussion will focus on the learning competency, explain how the products of weathering are carried away by erosion and deposited elsewhere. At the end of the lesson, you should be able to 1. Explain how weathering, erosion, and deposition occur. 2. Identify agents of weathering, erosion, and deposition. Earth's surface is covered by rocks. These rocks undergo a series of geologic processes known as the exogenic process. This includes weathering, erosion, and deposition. Now, how are these three processes connected? Let's start with weathering. Weathering is a process by which rocks are broken into smaller fragments chemically or physically. This process is due to rocks' exposure to varying temperature, pressure, substances, and biological actions. Weathering can either be mechanical or chemical. Mechanical weathering happens when a large rock breaks into pieces physically without alteration in its chemical composition.
There are a number of ways mechanical weathering can happen naturally. Frost wedging is a process where water fills cracks or holes in a rock during the day, and at night freezes. Since frozen water has a higher volume than liquid water, as the ice expands each night, it wedges the cracks or holes open deeper. As rock is broken off, pieces fall and collect at the base of the cliff below, creating a tailless slope, a good clue that frost wedging is happening above. Exfoliation is a process where a rock is unburdened by its overlying rocks during erosion. The result is a reduction in pressure. Under less pressure, the surface of the rock expands outward and can shed layers like an onion. A form of exfoliation can also happen when the surface of a rock is heated up during the day and expands, and then cools at night and contracts. The continual expansion and contraction can weaken the outer layer of a rock and make it shed in onion-like layers. Mechanical weathering can also be increased when the roots of trees and plants grow inside cracks in the rock and wedge them open larger. Tide pool organisms such as sea urchins can dig holes into a rock and increase the rate of mechanical weathering.
On the other hand, chemical weathering requires chemical reaction between rock minerals and other substances in the environment in order to break rocks.
Three major types of chemical reactions can occur during those interactions, including dissolution, oxidation, and hydrolysis. Dissolution happens when the atomic bonds in glass or a mineral or shell are broken by water molecules. Polar water molecules will pull apart ions from solid crystals and surround those ions in hydration spheres. These hydration spheres keep the ions separated so they can't recombine. The ions stay dissolved in the water as long as there is enough water to keep them separated. The opposite of dissolution is precipitation, the combining of ions to form solid crystals that settle out of water. Precipitation happens when waters rich in dissolved ions evaporate, taking the water molecules away and allowing the ions to find each other again. If the water involved with dissolution is flowing water like rainwater or river water or waves, the dissolved ions will be removed from the rock and the environment and taken to a new environment where precipitation may later happen, as, for example, a cement between sediment grains. Oxidation happens when oxygen in the atmosphere gets together with dissolving ions and creates a new oxide mineral, such as iron oxide or rust. This new oxide will coat the surface of the rock where the dissolution was taking place. We see evidence of oxidation when we see stained surfaces on rocks. These stains will come in a multitude of colors depending on which ion oxidized. Iron oxides can be yellow, orange, red, or brown, depending mostly on how much oxygen is available. Manganese oxides are black. Copper oxides are bright blue. Iron oxides are the most common oxides found on the surfaces of rocks, and usually when you see a red-colored rock from a distance, you're looking at the oxide stains on its surface. Hydrolysis happens when water interacts with a mineral that contains aluminum, Al, oxygen, O, and silicon, Si. During dissolution of such a mineral, the water will react with the ingredients to form a new clay family mineral. For example, when potassium feldspar reacts with water, it forms the clay mineral kaolinite. Clay minerals are often white, though they can come in multiple colors. And the crystals that form are microscopic, so they end up appearing like a fine powder, like grains of flour. This image shows kaolinite, the white powder, forming along the edges of an altered potassium feldspar in a granite. Of course, as mechanical weathering increases, so too does chemical weathering, and vice versa. Chemical weathering happens faster when there is greater exposed surface. When rocks break down into smaller pieces through mechanical weathering, they now have collectively a much greater surface area. The more chemical weathering that occurs, the more pits and holes in the rocks as minerals dissolve or turn into easily eroded clays, which gives more opportunity for things like frost wedging to occur. Another thing that can speed up chemical weathering are acidic waters. The most common naturally formed acid is carbonic acid, which forms whenever carbon dioxide mixes with water, a common occurrence in all natural waters on Earth's surface. This acid is what makes carbonated beverages acidic, and what can thus increase the acidity of your stomach when you drink sodas in high amounts. Waters rich in carbonic acid will make chemical weathering happen faster. What else can speed up any kind of weathering? The rock type and the climate or environment. Minerals with the strongest covalently bonded silicon-oxygen tetrahedra, such as quartz as described already, have the strongest bonds and are least likely to be dissolved by water. Chemical weathering will happen very slowly with these minerals because it's so difficult to break through the bonded tetrahedra, both physically and chemically. On the other hand, minerals with weaker ionic bonds will dissolve more readily, as will minerals with good cleavage. So the minerals in a rock will determine in large part how fast it will weather. In addition to the rock type, the environment makes a big difference in weathering rates. Chemical weathering requires water, so the wetter the climate, the more chemical weathering will occur. Heat speeds up the rate of chemical reactions, so hot, wet climates have the highest rates of chemical weathering. Cold, dry climates, like at the poles or at high elevations, have the slowest rates of chemical weathering. And of course, climates with regular freeze-thaw cycles will have increased rates of frost wedging. Climates with hot days and cool nights, increased rates of exfoliation.
The type, extent, and rate of weathering are affected by the following factors: climate, rock type, rock structure, slope, and duration of exposure. Now let's discuss erosion and deposition. Erosion is the process when rock particles are moved from one place to another. As agents of erosion carry the rock particles, they lose energy until such point that they can no longer hold them. Rock sediments are then dropped to certain locations, usually of lower elevation. This process is called deposition. Sediments are dropped off by agents of erosion. Erosion takes place due to the following agents. Water. This occurs from the chemicals in the water and the force and flow of the water. Water runs over the ground, carrying with it rock particles. This surface runoff eventually enters a body of water such as streams, lakes, and oceans. Next is wind. Loose rock and soil particles are carried away by wind and are deposited at other places. Wind is capable of transporting light particles over large areas thousands of kilometers away. Glaciers. large mass of ice and snow that forms in colder parts of the world. As glaciers move across land, they erode solid rocks and deposit eroded material somewhere. And gravity, a major force that drives erosion and deposition. Soil and weathered materials in high elevations like hills and mountains are pulled down by gravity. Loose rocks on a steep slope may roll downside and deposit materials at the base.
Once rocks have weathered, the weathered pieces can collect on Earth's surface in low-lying areas. They can get picked up by the erosional agents of running water, glaciers, wind, gravity, or humans, and moved along to a new surface where they settle out. During the process of movement at Earth's surface, the erosional processes, the pieces will continue to break down chemically and physically, such that after many hundreds of years and many hundreds of kilometers from their place of origin, what's primarily left are the finest sands and muds, made of the most resistant material. The two most abundant minerals that are found in these long-traveled mature sediment piles are quartz and clay. Because sediment piles will vary around the planet depending on the materials that feed into them, they all have a fingerprint, a distinct character of varying grain compositions, sizes, shapes, and sorting. We can describe those characteristics and use them to interpret the travel history and maturity of the sediment. For example, as sediments migrate downhill towards low-lying areas, especially if carried by running water, they knock about and get smaller and rounder. If deposited by waves or rivers in the normal course of movement, they will do so because of gradual slowing of the water, and thus only grains of the size no longer able to be carried due to the drop in velocity will settle out. So all the grains in a given pile of river sediment, alluvium, will be the same size. And all the easily rusted, dissolved, and hydrolyzed minerals will be gone, leaving only the most stable ones. Note, when sediments are transported by glaciers, they are trapped in the ice at the base of the glacier and so don't knock about so much or weather. Glacial deposits known as moraines form when glaciers melt and leave the sediment they carried behind in one big pile of unsorted, angular grains of all sizes, very different from river-deposited sediment. Sometimes a flash flood in the mountains or an avalanche of sediment off the continental shelf will pick up grains of all sizes and then drop them all at the same time at the foot of the slopes where they hit the flat valley floor. In these cases, as the water movement stops quickly and the grains settle in one spot, the largest, heaviest grains will settle out first, followed by smaller and smaller ones. This settling can result in a texture in the sediment called graded bedding, which, if buried by additional future deposits, can eventually be turned into rock, retaining fossil evidence of the past graded bedding event. Ultimately, all these described piles of sediments of varying maturity will turn themselves into rocks, either through compaction or cementation. Compaction happens when mud-sized grains are squeezed, water is released, and the clay particles within stick together. Cementation happens when groundwater's rich in dissolved ions percolate through the grains. Eventually, as the water leaves or evaporates, crystals are left behind. These crystals will grow between and cement together the grains. Examples of common cements include hematite, rust, calcite, and quartz.
And that ends our lesson. Congratulations!